Hey gang, just me today, Matt. Sorry, PJ's not in this video. We finally got rid of him. Actually, he's right over here in the room with me, watching me strangely creepily. Anyway, this is the first of 3 videos about science stuff, essentially. This video is about the InSPIRESS mission background, gives you an overview of Europa and a very quick overview of Jupiter. Everyone's going to watch this video. The second video in this trilogy is about potential science objectives on Europa and on Jupiter. And this video and the next video tie in very heavily. Everyone's going to watch the second video too. So I'm actually going to talk about some of the things, I'm going to tell you about some of the things that are potential science objectives, and then in the next video I'm just going to kind of reiterate those and explain how those could be science objectives. And then the third video is strictly for the design group, and it talks about, I will talk about instrumentation and science instruments, how they work, which instruments to use to measure which things, stuff like that. And kind of an overview as well. I won't go into a lot of detail, but you'll see it. So, but this is for the design group. You guys are the lucky ones. Okay, so I'm going to jump right into this. People complain about these videos being too long, so I'm going to try to do them quickly. The outline today is going to go over the mission background, just the InSPIRESS mission, the trajectory, how it's going to work, where the spacecraft are going to go, that type of thing. Europa, we're going to give you an overview of Europa, a real quick overview, tell you what's important about it, why it's an interesting place. And then Jupiter as well, just a quick overview of Jupiter and tell you why it's interesting and some potential things you could study at Jupiter. The background, okay, so this is not to scale, by the way. Earth would be the great red spot on Jupiter is 3 times the size of Earth. You could fit 3 Earths in there. So yeah, it's not to scale. However, this gives you a representation of the trajectory. So we're going to leave from Earth. Normally, when we leave from Earth for an outer planet, and the outer planets are Jupiter, Saturn, Uranus, Neptune, Pluto. The spacecraft has to do flybys of the inner planets. Like normally, when we do this, we'll take off from Earth and head toward Venus, and then go around Earth and Venus a couple of times to get speed, to gain momentum. Essentially, we're going to steal momentum from Earth and Venus, and then it slingshots us out to the outer solar system. Right? That's the way we normally do it. However, on this mission, we have a new launch vehicle called the Space Launch System. Well, that's the name of it right now. They're going to rename it, I think. We call it SLS, and it's being built, designed and built in Huntsville, Alabama, at the Marshall Space Flight Center right now as we speak. It's really cool. We showed it to you. We showed you the models when we came to your class on the live intro visit. We showed you the model of the Atlas V-401, which was the smaller launch vehicle, and then the big one was the SLS. And it's actually bigger because they were at different scales. Anyway, so the SLS is so big and powerful that we can do a direct trajectory to Jupiter, and it saves us a ton of time. Okay, that's the advantage of it. So we do a direct trajectory to Jupiter. It takes us. Jupiter is still far away. Earth is 1 astronomical unit from the sun, 1 AU, because we defined what an AU is. So we said Earth is 1 AU. Okay, Jupiter is 5 AUs. It's 5 times the distance from the sun as Earth is. Earth's about 93 million miles from the sun. So Jupiter is about 5 times 93 million miles. So basically 500 million miles. That's how far Jupiter is. So, take off from Earth, direct trajectory. So it takes 1.9 years to get to Jupiter just flying directly, which is pretty far. And once we get to Jupiter, we're going really, really fast. So we got to slow down. Now, in propulsion and rockets and stuff, you can slow down quickly, but it takes a lot of energy, a lot of propellant, and propellant is mass, and you don't have much mass on a spacecraft. So you can also slow down slowly, take a long time to slow down. It takes a lot less mass, but it takes a lot more time. In this case, we've chosen to slow down slowly because once we get there, we want to make sure we have as much mass to dedicate for the science as we can. We don't want to put mass toward propulsion and toward gas, essentially. So direct trajectory, 1.9 years, and then we spend about 700 days. So actually more than the direct trajectory, about just shy of 2 years. Actually, that might be the same time. 700 days and 1.9 years. I'll have to look that up. So 700 days, slowing down and doing flybys of Jupiter. We do about,
693.
huh?
693.
So yeah, it's about the same length. So it's about the same length of time here and then the slowdown. So after about 4 years, we'll end up at Europa. Again, it takes a long time to get out there. It's a long way away. So we do about 16 flybys of Jupiter while we're slowing down. And what actually is happening physically is we fly by Jupiter. We fly by close enough that Jupiter steals momentum from the spacecraft, which is what we want. You know, normally on those flybys, when we fly by Venus, we steal momentum from Venus and Earth to fly out to Jupiter. But in this case, we're going to have Jupiter steal momentum from us. But don't worry, it's insignificant as far as Jupiter is concerned. Jupiter is so big. And then we will eventually get into orbit around Europa. So what this does, the reason I'm telling you this trajectory is you guys have 3 basic options for science objectives, 3 basic places where you can do science objectives. First one is Europa, obviously. That's our planet of interest here. The second one is Jupiter. You can do science at Jupiter. You can look at different aspects around Jupiter. We're going to have 16 flybys. We'll talk about that in more detail. Or you can do science at the space, the interplanetary space along the trajectory somewhere. So if there's some interesting stuff outside of Jupiter and Europa that you want to look at that's just in space, go for it, you know. Or between Earth and Jupiter, go for it, whatever. It's your call. I think the more interesting stuff might be around Europa and Jupiter, but you guys are in charge of your science. So the elements we have, when we say spacecraft or we say elements, it's the same thing. This mission has 2 different elements or 2 different spacecraft involved. The first one is an orbiter, and it orbits. The second one is a lander, and it lands. So like I said, it's a 1.9 year cruise to Jupiter, and then the lander is attached to the orbiter during this part. And then during the slowdown, the 700-day capture around Jupiter, there's 16 flybys at 100,000 kilometers away from Jupiter. The lander's still attached to the orbiter. Then it eventually ends up in a 30-day, 100-kilometer polar orbit around Europa. Polar meaning it goes from North Pole to South Pole. It goes top and bottom around Jupiter. Around Europa. Sorry. So what that means is the spacecraft is going pole to pole, and at the same time Europa is spinning underneath it, right? And so the cool part is a polar orbit means that you'll eventually see every single spot on the surface of Europa, because it's going to spin underneath. It will spin underneath you as you go around it. Do you see this? My little graphic here with the Dr. Pepper bottle. Anyway, not a graphic, but whatever that is. So that's the polar orbit. That's the significance of a polar orbit. And the other significance is on the south pole of Europa is where they have those plumes. The lander is going to land, going to be near the equator, and it's going to be on the non-Jupiter facing side of Europa. And I'll talk about what that means in a second. But it also lasts for 30 days. So once this guy gets into orbit, the lander drops off, and they both last for 30 days, and then they die. And then this guy's going to crash into Europa or something, kill some fish. So basic overview. If you have any more questions, let us know, or talk to your POCs. So Europa is the 6th moon from Jupiter that we know of right now. Jupiter, I mean, there could be more moons, they just haven't seen them yet. When it was discovered by Galileo Galilei in 1610, he thought it was the 2nd moon of Jupiter because he only saw 4. He saw the 4 Galilean moons. The 4 Galilean moons are Io, Europa, Ganymede, and Callisto. And so at the time, Galileo did not name the moon Europa. He named it Jupiter 2. So sometimes it's still referred to as Jupiter 2, even though it's the 6th moon of Jupiter, because they thought it was the 2nd moon of Jupiter. Anyway, and that's how it got its name, and it's the 6th largest moon in the solar system. It is slightly smaller than Earth's moon, than our moon. The gravity on Earth's moon is 1/6 Earth's gravity. Gravity on Europa is about 1/7 Earth's gravity. That's the multiplier for 1/7 roughly. Europa's covered in ice, like we've talked about before. It's got these kind of orangish parts too that we'll talk about in a minute. And it's got a subsurface ocean. That's the most interesting thing about Europa. They think it has a subsurface ocean. They've never actually seen it, obviously, but they think it's there. They've seen indicators of it. This is an artist rendition or an artist drawing of what they think Europa looks like. it is one of the flattest moons or planets in the solar system. There are very, very few craters, very, very few mountains and hills on Europa, which makes it very interesting because the more craters a planet or a moon has, the older they think it is. So the fact that Europa is pretty flat and has very, very few craters, they think the surface is pretty young, okay? That's consistent with this subsurface ocean idea. They think that it's kind of regenerating itself. Also very few mountains. They do think it has these spikes, and these spikes that are in this drawing here, this artist's interpretation of Europa, they think those spikes are, 10 meters, maybe the size of some small buildings or so. And 10 meters is what, 30 feet? So that's like a 3-story building. So maybe 3 stories tall, something like that. So it's not small, but it's still not a mountain, right? And it's not a big crater. The orbit of Europa is very interesting and leads to some of its cool stuff too. So it's tidally locked. Now, a second ago I said that there was a Jupiter-facing side and a not Jupiter-facing side, right? There's a side that faces Jupiter and the side that does not face Jupiter. This is just like Earth's moon. Our moon has a side that faces Earth and a side that faces away from Earth, okay? With all due respect to Pink Floyd, there is no dark side of the moon, our moon. It's a great song, but all sides receive light. I'll explain that in a second. So, tidally locked means that there's one side that always faces. So if my head is Jupiter or Earth, whichever one you want to call it in this scenario, and my fist is Europa or our moon, it spins on its axis just like a planet does, but it spins at the exact same rate that it goes around the planet. So it doesn't look like it's actually spinning, but it is. So this is what happens. As the planet spins, the moon is also spinning with it. So there's a side that always faces the Earth, or a side of our moon always faces the Earth, or a side of our moon always faces Jupiter. I keep hitting my nose. It's very large. Anyway, so that's called tidally locked, which means that its rate of rotation equals its rate of revolution. So a lot of moons are like this. Io, Europa, and Ganymede are all three like this. The last moon and the last of the Galilean moons, Callisto, it's a free spirit. It doesn't do what it's supposed to do. Europa's orbit around Jupiter, and it kind of defines, it gives it a lot of interesting features. The tidal heating is, first of all, it's an 85-hour orbital period. It's about 3.5 Earth days to get around Jupiter one time. So that's how long it takes it to spin on its axis, is 3.5 days, and that's how long it takes it to get around Jupiter one time. And while it goes around Jupiter, its orbit is not exactly circular. It's not perfectly circular. It's close to circular, but it's not perfect. And so there's times where it's closer to Jupiter, and there's times where it's farther away from Jupiter, right? So when it's closer to Jupiter, Europa feels more gravity from Jupiter, okay? So it's squeezed. It's kind of like, I should have brought a balloon. It's squeezed like a balloon. That's what this graphic is trying to show. It's squeezed. And then when it's further away from Jupiter, it's not so much squeezed, right? It's more so the planet goes sort of like an ellipse, like an egg, and then it goes to sphere, egg, sphere, egg, sphere. And this is this egg, sphere, egg, sphere.
It's what?
Egg, sphere.
Squeeze.
Squeeze. Squeeze. And so what this does is it heats the inside of the planet. Take a paper clip, right? Take a paper clip, bend it a lot, bend it. Before it breaks, what does it do? It gets hot, right? It heats up because of the bending. The same exact thing happens on the inside of a planet. It's being smushed and pulled, squeezed and pushed, squeezed, and it's kind of getting beat up. Io gets beat up more. Io is like a terrible, terrible place. There's volcanoes everywhere. It's so hot on Io because it's being squeezed so much because it's so close to Jupiter. But Europa is far enough away from Jupiter that it squeezes it just enough to heat the inside of the planet. That's why they think there's a liquid water ocean underneath this ice layer. They think that the inside of the planet, the squeezing, this tidal heating, they think it provides heat to keep the water from freezing. Which is cool because where there's water, there's typically life, okay? Which is why they think there's life on, there's three things that involve life. I'll talk about that in a second. But water is one of the main things that is we need for life. So Europa's been stretched and pulled. This causes internal heating. There's also tidal heating happens on many planets. It happens on other moons all over the solar system with the large planets, like around Saturn and around Jupiter. Now, the first 3 Galilean moons have a very strange orbital mechanics. They have a resonance, is what it's called, basically. And if you want to do it, they're perfectly ratioed, which is very weird, but it ends up making, and since Europa's in the middle, it's Io, Europa, Ganymede, what it ends up doing is it makes Europa even hotter than it would be with just tidal heating. Because Io goes around Jupiter at a 1-to-1 ratio, okay? Europa goes around 2-to-1. So basically every 2 times that Io goes around Jupiter, Europa's gone around 1 time. And it's almost exact as far as that resonance. So 2 times for Io to go around is 1 time for Europa. So what that means is they line up a lot, okay? And then Ganymede is a 4-to-1. So every 1 time Ganymede goes around Jupiter, Europa's gone around Jupiter twice, and Io's gone around Jupiter 4 times. So what happens is these planets, these moons, line up ever so often with Jupiter, and the combination of that lining up, see, the moons also have gravity, so they'll help pull Europa away, or they'll pull Europa toward, like Io will pull Europa toward Jupiter because it's in front, it's between Jupiter and Europa. So Io is going to add to the gravity that Jupiter pulls, and then Ganymede is going to pull it away, so it's got more pulling because of this resonance. That's what this resonance is all about. And basically that creates more tidal heating inside the planet. So it's inside the moon. So Europa is actually quite warm on the inside because of this constant flexing that it experiences. It's really kind of cool. So that's the orbit. Great, right? There's a video, you guys, I'm going to splice into this video. It's a 3-minute long video, and it shows an animation of this, which you'll like. So Europa's atmosphere, very, very small atmosphere, very thin, very tenuous atmosphere, almost non-existent, but it's there. Very thin. It's mostly oxygen. Okay. What happens is the surface of Europa is ice. It's frozen H2O, water, ice. That's what they, frozen water, basically what it is. And so radiation from Jupiter pummels Europa a lot. Pummels the one side of Europa at least. And there's magnetic fields. Jupiter has a very strong magnetic field also. And so what happens is that the radiation from Jupiter hits Europa, and what it does is it causes reactions on the surface with the water, okay, with the frozen ice, with the frozen water, and it causes a dissociation reaction. What it does is basically it frees up oxygen, and oxygens are allowed to float, and so it creates this thin atmosphere around Europa, and the pressure is 1 micropascal. It's 10 to the minus 12 lower than Earth's, and it's very tenuous. It's very non-existent, but it's interesting because of how it's created. It's created by the radiation from Jupiter, and scientists also believe that there's other. There might be life on the surface of. Or life containing or life building substances, elements on the surface of Europa that were deposited there from asteroids or meteors, or from the plumes that we'll talk about in a minute. And so this disassociation, this reaction with the radiation from Jupiter, it actually is very interesting because if you were to study the atmosphere and see other things besides oxygen, you could determine, okay, these other elements are also on the surface. These elements that are associated with life are also on the surface. So you wouldn't actually have to touch the surface in order to determine some elements that are on the surface, because of the radiation is causing these elements to gain energy and go into the atmosphere. Does that make sense? So we'll just go on, just say it does. So the surface of Europa is very interesting. Again, it's ice. It's one of the smoothest, like I said, in the entire solar system. Very few mountains or craters, these 10-meter tall icy spikes. And albedo, it's got a high albedo. Albedo means it's very reflective. Basically, you know, white, like this whiteboard behind me has a high albedo because it's extremely reflective. It's not the most reflective thing in the solar system, but it's actually highly reflective. I think the albedo is like 0.6. It reflects 0.6 of the light that you know, 60% of the light that it hits it. The surface, they think, is between 20 and 180 million years old. Big swing there, right? So they say it's about 65 million years old, the surface is, which for a planet or a moon is very, very young. You know, Venus, the planet that's closest to Earth, they think it's got a young surface and it's 500 million years old, right? And so 65 million years is very young for the surface of the planet, which is one of the reasons why they think that the surface is regenerating because of the subsurface ocean. The temperatures at the equator are basically minus 260 degrees Fahrenheit, and the poles are worse. They're minus 370 degrees Fahrenheit. That's really cold. That's like worse than North Dakota. So, and again, high radiation on the surface on the side that faces Jupiter. It's, if you know anything about radiation, it's 540 rems per day, which would kill you within a day, would kill a person within a day. So I wouldn't visit. Europa, one of the cool things about Europa, it's very smooth, as we said, but it's got a lot of interesting surface features because they think there's this subsurface ocean and there's ice. So basically the surface is ice. And so the ice has some interesting characteristics because of what's beneath it, okay? So this is a graphic that shows there's what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different features. These two are just different. That's the whole, and that's the IR view. So these are described in your engineering design notebook, so you can go read these. I'm not going to go into all these, but basically what it amounts to is one of the interesting things, well, I'll get to in a second actually, is these ridges. Since it's ice is solid, right? It's supposed to be solid. And like I said before, Europa is squeezed and pulled and squeezed and pulled. So what happens if you were to do that to a solid, right? It would start to crack, okay? So that's why Europa is filled with a bunch of cracks, basically from Jupiter going, you know, Jupiter's just beating it up. And so squeezing, that's causing these cracks in the surface. They run all over the place. They're called lineae. And there's other, these terrains, they call these chaos terrain and stuff like that, basically. There's a few craters, but these lineae are the ones, the ridges in the lineae are very interesting because they tell us some other things about Europa. And then there's these flows that they have as well. So again, this is in your engineering design notebook. Read about those, and you can look online too. So these are the lineae that I just talked about. So scientists actually pretty much know that the surface of Europa is spinning independently of the planet spinning itself. Okay? So if you were to have a solid sphere like a planet that was ice, right? And you were to flex it, squeeze it the same direction every time because it spins, it always faces Jupiter in the same way, and Jupiter squeezes it the same way every time, right? And the planets and the other moons line up with it the same way. They've lined up with it the same way that they've been doing it for millions and millions of years. It's been doing the same thing for at least 65 million years, right? So you would think that these ridges, these cracks in the planet would all line up and go the same direction, right? Because it's being squeezed the same direction every time. Squeeze, squeeze, squeeze. But they don't. You've got them going, they're at right angles to each other, okay? You've got them going all over the place. What scientists have figured out, and they actually did this from photos from Voyager and Galileo, the spacecraft, those two spacecraft that flew by Europa and took pictures of it. They've been able to determine from those spacecraft that the surface is actually slowly rotating independently of the planet rotating. So there's some text here, but basically they think that that the surface will rotate all the way around independent of the planet rotating itself, but it takes it 12,000 years. So it's a long time. It's not going to happen like during our lifetime or anything, but it's kind of cool though. And the reason, and this goes back to the subsurface ocean. Excuse me. The icy shell, the icy outer shell can do this because beneath it, it's not fixed to the planet because beneath it is an ocean. So the icy outer shell is just free to move about, right? Because it's not statically attached to the planet that's rotating. So that's another reason, that another piece of evidence that goes to show that there's a subsurface ocean. Again, they've never seen it, they've never been to Europa, we've never set anything on Europa, they've flown by it, they think there's a subsurface ocean, they've seen indicators of it, and, okay, the surface colors should be white, okay? The surface of Europa, this is a false color, should be white, basically all white surface, right? Because it's ice, it's all ice. It's water, it's frozen water, so it should be ice, it should be white. There's these obvious orange, darker regions that they call it. Some are orange or maybe even like a reddish color. And this is kind of accentuated, what they do with, this image has been, you know, kind of messed with just to show the lineae and the darker regions. But there are definite darker regions on the surface. Spacecraft have detected, they've flown by these as they're looking at other things. They fly by and they use remote sensors to you know, what are these things? What are these little blotches? You know, what is this? Looks like a bruise, or like some, you know, like a bad, this could be like some, like a really bad, you know, skin, you know, picture. It's gross. But the areas, what they think it is they think there's higher mineral content in those areas. They think that they're rich in salts, like magnesium sulfate, sulfuric acid, you know, sulfur kind of things. But these are also, a lot of the things they've detected are also colorless. So it still should be white. And now it goes back to the radiation, this dissociation that's happening with Jupiter. So they think that there's some interesting interactions going on the surface that they basically don't understand what's going on the surface completely. But they have detected salts and some sulfurs, stuff like that on the surface using remote sensing, but they don't know exactly what these are made of. The sulfur compounds are suspected to give the dark color, but they're not exactly sure what's going on. So it's some interesting stuff. There's a planet, I mean, there's a moon here that's supposed to be completely ice and completely white and reflective, but there's these dark spots and they don't really know what it's about. So they probably won't know until they go and actually touch it and sample it. So impacts, like I said earlier, very, very few craters, but there are a few, okay? And there's one in particular that's very interesting. It's near the equator on the non-Jupiter, right now the non-Jupiter facing side, and in about 6,000 years it'll face Jupiter. But on the non-Jupiter facing side, there is an impact crater where scientists believe that an asteroid or meteor impacted Europa a while ago, because they detected what philosophicates, I don't know, whatever. Organic material is what they call it. NASA they've done flybys and they've detected this stuff, which they consider organic material. It's clay-like materials, but they don't think it's natural. They don't think it occurred naturally by itself on Europa. It didn't come from the inside, they don't think. They think it was deposited there from an impact, because there's this 25-mile wide ring, which is approximately 75 miles away from a 20-mile diameter crater, okay? So there's a crater, 20-mile diameter crater, pretty good-sized crater, right? Not very many of them, but this is a good-sized crater. And then 75 miles away, there's a 25-mile ring of debris. So what they think is this meteor or asteroid hit the surface at about a 45-degree angle and then spread debris way down, down the street there. So that's what they think happened, but they're not sure. They don't know what this stuff really is. Is this how, scientists are wondering, oh, is this how life, goes around the universe? How, meteors carry it around and it hits, and then it, and that's how they populate the, universe with life. Is this how it happens? Scientists are wondering this. But if it was an asteroid, it was likely about 1,100 meters in diameter. If it was a comet, which are, comets are kind of icy and lots of empty space inside, they think it was about 700 meters in diameter. But the content and origin are not known. They don't know what's going on. They don't know where this thing came from or what exactly it's made of. But they have detected these clay-like organic materials on it, which is, I think it's cool. I love it when there's stuff that we don't know, because we think we're so awesome, like, yeah, we're smart, but there's, here's a moon that might have life in it and on it, but we don't know yet. So, very cool. So the most interesting thing about Europa is The subsurface, the stuff we can't see. That's where they think the ocean is, the subsurface ocean. They actually think it's a salty ocean because they detected magnetic fields around Europa. Europa does not create its own magnetic field like Earth does. It has what's called an induced magnetic field. Basically, Europa exists in Jupiter, right next to Europa, right? Jupiter, biggest planet in the solar system. All planets can fit inside Jupiter, still have room. Jupiter was almost a sun. It just no one lit it. And Jupiter has a huge magnetic field, and Europa is sitting inside of it. And so this saltwater ocean that they think is below it is moving around. And so you have this moving conductor in this magnetic field, so it induces a magnetic field on Europa by itself. But they know it's not a magnetic field of Europa because of the measurements they've taken around it on the different spacecraft that have flown by. So this shows, again, in the previous slide, I talked about there were, what, like 15 or so different surface features of Europa. Here's a few of them right here, and here's what scientists think have caused those surface features based on what they think is below. Again, they think there's this hard icy shell on top. They think that below the icy shell it's a little warmer, so they call it warm ice. You know, so yeah, it's a little warmer. It's warm ice, whatever. They think it's just ice that allows more water to come into it. It's not as solid as, I mean, this is like solid ice. And then down below, they think is actually water. It's just not frozen at all. It's just actually water, and they think there's salt water. And then down below that is, this is key, is the water comes in contact with the surface, the actual surface of the planet. So that's what they believe right now. And so again, the surface features are a direct result of what's below. That's why I like this picture a lot. That's why I put it there. So internal structure-wise, like I just said, they think that, do I have the, yeah, I have the, yeah, okay. They think that there's a subsurface ocean underneath. They think there's hard icy shell and then some warm ice, not as hard ice basically, and then they think there's just water, and then they think there's an actual surface to a planet, rock, stuff like that. So that's what these pictures are supposed to show. And then very, very deep inside is the metallic core. It's not a moving core like ours, like Earth's core is this molten core. Theirs is just a solid metal core. But there's a rocky interior that the liquid water touches. So they believe the ice, if you total up the water and the ice and then the hard ice on the outside, Europa has, the volume of water on Europa is about 2 times the volume that Earth has in its oceans. That's a lot of water, considering how much bigger Earth is than Europa, right? A lot of water on Europa. So it's believed to have an outer layer of water, and then some of that water is the topmost layer is frozen, and then there's this warmer ice. And so it's up. They think it could be up to 170 kilometers thick. 170 kilometers. That's very, very thick. That's like from the surface. Where does space station fly? Where does it fly? 180 nautical. Yeah. So it's actually 170 kilometers. It's lower than space station. A little bit lower than the space station, but it's still in space. 100 kilometers is considered the edge of space from the surface of Earth. So that's a lot of water. So again, I was saying that there's an induced magnetic field because they think there's this ocean, this saltwater ocean that's moving around below the surface. Europa's surface features suggest the ice, like I showed in the previous slide, and the moving outer shell. The shell, the fact that Europa's crust, the outer shell that we can see and we've taken pictures of, is moving independently of the planet rotating. That's also another indicator that there's water beneath it. So all these things are indicators of water beneath it. So now, I know you guys have been keeping track of this on like Facebook and Twitter and stuff. It's been a huge debate. I know you guys are, and I don't want to start anything in your classroom because I know that some of you guys in the classroom are one side, some of you guys are the other side. So it's almost as bad as like Bama, Auburn type deal. But there's the thick ice versus the thin ice debate for Europa. I know you've been keeping up with it, so please don't. I don't want to cause anything in the classroom. I don't want to cause any disturbances. So again, they think the ice is probably around 150 kilometers deep, right? Or the water is. Total, that includes ice. So the great debate is that the thick ice, they think that scientists think that there's a very hard layer of about 30 kilometers of solid ice, just pure, basically it's as hard as rock, okay? Because it's so cold, okay? And then below that, there's 100 kilometers or so, maybe a little bit less, 80, 100, whatever, of this warm ice, okay? That will move about, kind of like, you know, it'll convect, it'll move around this ice slowly, not like water, but it still moves. And then below that, you know, whatever the rest is, 50 or 30 or whatever kilometers is the actual water, the salt water. So that's what most scientists believe. However, there are some scientists, the crazy ones probably know, that believe that the ice is actually very thin. That they believe the ice is 200 meters thick, the solid crust is just 200 meters thick, and then below that it's just water. They think that. They think it's just 200 meters of thick ice and then just water, okay? Most scientists do not believe this because of the surface features on Europa. But some scientists do believe it because of some of the measurements that were taken way back with Voyager and Galileo. There were some measurements that were taken that possibly indicated a thinner ice shell than what scientists thought at the time. However, those were localized measurements. There's some things with that. But there's a great debate, and I know I don't want to start anything in a classroom, but so basically, everyone agrees that there's water under there, okay? They just don't know how thick the ice is. And if it's thin ice with water, or if it's thicker ice with water. So, however, most believe the thick ice theory. And again, very important part of this is that the actual water, the non-frozen water, the salt water, touches this rock part of the planet, touches the rocky inside of the planet. So, that's a good segue, Matt, thank you. So, life on Europa. Is there life on Europa? There are three basic things that you need to have for life. As we understand life today, like right now, as we understand life, there are three basic things that you have to have life. You have to have water. That's what this triangle is about. It looks kind of like a Illuminati or something. But you have to have water. Water creates an environment for chemical reactions. You have to have essential chemical elements. That's what this is, chemistry. You have to have chemical elements that are critical for biological processes. You need, you know, carbons and carbon-based life form, right? You need carbons, you need some sulfurs, you need some other elements, not just water, not just hydrogen and oxygen. That's boring life, right? That's just water. You need some other elements in there to create the life, right? And so that's why it's important that the ocean touches the bottom of the sea on Europa is rock. That's why it's important, because those are your essential elements. Those are your carbons and your sulfurs and your other elements that are needed for life. And then energy. You got to have energy. The energy that could be utilized by the living things. Living things require energy to live, right? And so, so Europa has a liquid water ocean, and this water ocean comes in contact with the rocky surface of the planet. There's the water interacting with the chemistry, and then the tidal flexing, and also there might be some energy stored inside the planet, like just there might be some molten material inside the planet. They don't know exactly, but the tidal flexing should be enough energy. Also, should be enough energy to create life. So Europa has the triumvirate of the three things that you need to create life. And so that's why scientists believe it's the most promising, besides Earth, obviously, it's the most promising place in our solar system for life. And again, not going to be like you're going to land there and say that someone's going to say, "Hey, how are you? Been waiting for you. It's been a while. I've been sitting here and it's cold. Here's a coat." It's not like that at all. It's not going to be life forms like us. It's going to be life like at the bottom of the ocean, the bottom of our ocean. Very primitive life. But there is stuff that lives at the bottom of our ocean near vents where it's warm and stuff. There's stuff that lives down there. Very weird stuff, but it's stuff in general, okay? So that's why scientists believe there's life on Europa. Or it's very promising at least. So, another interesting thing, I like it because they just discovered it. And the reason this was discovered by a student, okay? So there you go. A graduate student in Germany, I think, discovered this. He walked into his advisor's office, and he didn't care about Europa at the time, and he said, he basically said in German, he said, "I need a thesis topic. And the advisor said, here are some old pictures from, gosh, where was it? I can't remember which mission it was. I want to say it was Galileo mission. Here's some old pictures from the Galileo mission of Europa. There's some weird stuff going on around Europa. We're just not quite sure what's going on. Take a look at it. And so this kid, he's probably in his early 20s. This German kid, he's very German. He looks at these pictures and starts investigating, okay? And then notices some patterns, notices some things with the orbit of, Europa and Jupiter, that these strange elements that they were sensing around Europa only occur at certain times and only occur in certain locations. And so what he ended up doing is he got time. He actually got time, and they moved Hubble, and they used Hubble to take images of Europa. And with the combination of the pictures from Galileo, the spacecraft Galileo, not the man, but the spacecraft, and then the images from Hubble, they confirmed that yes, there are plumes of basically it's water essentially, but there's some ice in there. So they call these cryovolcanoes. There are volcanoes that shoot out frozen ice and water, basically. So there are these cryovolcanoes, plumes on the south pole of Europa that shoot out material into the. Europa is so big. I mean, for a moon, it's actually kind of big. It's the material doesn't leave. It kind of goes out and then falls back down on the planet. But what this does is it creates an interesting opportunity, because if we want to find life in the ocean, right? We want to find life. We believe there's life. There's life in the ocean down below, but everyone agrees there's a lot of ice. There's at least 200 meters of ice. That's a lot of ice. There's probably more like 30 kilometers of really hard ice, harder than rock ice, between the surface and the ocean, right? And so how do we get to the ocean? Well, we got lucky because the ocean is coming to us, okay? That's what this really means, is that these plumes are water somehow coming down from within Europa and being pushed out, and then it's going to land back on the surface eventually, because it's going to get pushed out and then going to fall back down. So they've done some rough calculations. They expect that these plumes reach 200 kilometers in altitude, and that when it's flowing, it's 7,000 kilograms a second, which is extremely high. That's a lot. It's a really high flow rate. So it only happens when Europa is farthest away from Jupiter. When it's close to Jupiter, it's being squeezed right. When it's close to Jupiter, it's being squeezed. And so what it does is basically the squeezing shuts the vents off. It squeezes the vents closed. But when it gets farther away from Jupiter, it relaxes and the vents open back up. Okay, so that's what's going on. Very, very cool. Very, very neat opportunity for us to sample the inside of Europa without going in Europa. Very neat. For those teachers and stuff, we did this like 2 years ago. We had Enceladus, and Enceladus had plumes. However, Enceladus didn't have the three things that were required for life. Enceladus did not have an ocean that was in contact with rock. Europa does. Enceladus was just a big ball of ice. So Europa has this ocean that's in contact with rock and has energy. So the likelihood of life on Europa is highest besides Earth in the solar system. And these plumes give us an opportunity to sample the inside of the planet without going inside the planet. So the source of the plumes, this is another artist, drawing and stuff. They think that it's coming directly from the water down there, right? And so they think there's cracks from this constant, pushing. They think they form cracks, and that it just pushes up and pushes out. Could be pockets. There could be pockets of there could be frozen, pockets of lakes that don't touch the rock. And if that's the case, then there probably wouldn't be life in those plumes. But if it's the same water that touches the rock, then there could be life in those plumes. It could come directly from the subsurface ocean. If this is the case, then there's possible biologicals in there. So that's Europa. Okay, boom, Europa. Icy shell, subsurface ocean. There's some weird stuff going on the surface. They don't know what's about. There was a possible impact from a meteor or an asteroid. They don't know what's going on there, or what the stuff was, where that asteroid came from. The subsurface, they don't know how thick the ice is. They don't know if there's biologicals, if there's life on this planet, on this moon. They don't know what's going on. Okay, So we're going to talk in a minute, like in the next video, we'll talk about potential science objectives based on these things. So Jupiter. Jupiter, biggest planet in the solar system, huge, huge planet. And what it's best known for is this right here, the Great Red Spot. Below it, you can see it in this picture, and then right here, it is the just the white spot. It would be, on any other planet, it would be called great. But on Jupiter, because this white spot's about the size of the Earth, okay? But on Jupiter, because it's got this great red spot, this white spot's just kind of like, what up? You know, it's kind of like, I don't know if y'all, Joe Montana and, you know, Steve Young. Steve Young, great quarterback, but Joe Montana, awesome, right? So kind of overshadowed Steve Young until he retired. So this is Joe Montana, this is Steve Young. Anyway, look it up, Wikipedia. So it's the 5th planet from the sun. It's the largest by far in the solar system. It's called the gas giant. It's basically, it's mainly gas, mainly hydrogen and gas and helium as well. Because the pressure is so high, the gravity is so great, once you get down lower, the actual gas turns into a liquid because the pressure is so high. So you'll have liquid helium and liquid hydrogen, which is crazy. And then when you get even lower, they think there's metallized hydrogen. They think the pressure is so high in the center of this planet that it's turned the hydrogen into a metal, into a solid. It's a lot of pressure. And so we'll never get there. The pressure's too high. We can't build something that can survive that. There's radiation and pressure. It's just, you know, it's bad, and it's real hot down there too because of the pressure. So extremely high pressures, very high wind speeds and storms. On Earth, Earth has, you know, we've got like our one basic jet stream that goes around Earth, right? One huge jet stream. We think it's huge. And they go the other way, you have the trade wind. So one jet stream, kind of like in North Alabama, it goes from the west to the east. So it hits Florence and then it goes to Huntsville, right? That's the way weather usually typically goes on Earth. Jupiter, lots and lots and lots of jet streams. You can see it's just being sheared. If you look at an animation, and there's lots of animations that show there's jet streams going this way and this way and this way and this way. And that's part of what feeds this basically huge hurricane on Jupiter is the jet streams, the counter opposing jet streams that go around. So weather-wise, nothing compares to Jupiter. Not a planet in the solar system compares to Jupiter weather-wise. It's just crazy. There's high winds, storms, lightning, all sorts of cool stuff. Lightning's from friction. You know, there's lots of friction in that atmosphere. And then if you get too deep, you just die because of the pressure and the radiation. But it's a very interesting place, really cool. The Great Red Spot, also very interesting, very cool. And the smaller white spot, lots of interesting measurements you can take there. I don't think we ever sent a probe into Jupiter?
Yes.
Which one?
Galileo.
Galileo went into Jupiter. Had a probe, sorry, that went into Jupiter. So we've sent a probe into Jupiter, but it's possible to probe more. This storm changes over time. It's been there since we've been looking at Jupiter, but it's changed in size, it's changed in location, shape, stuff like that. So there's interesting stuff to measure about Jupiter as well. Here's a diagram, a really cool graphic. I just like the graphic, to be honest with you. But it shows there's the cloud layer, there's the gassy layer, then you get lower, you have liquefied hydrogen and helium, and then the metal hydrogen. And this artist believes that there's an actual rock and ice core. Some people don't believe that. They think it's just the metallized hydrogen core. But some believe that in order to get that started, there was some sort of very dense rock core. So that's Jupiter. That's the end of this. That kind of gave you an overview. Remember, we had the InSPIRESS mission, the long trajectory to get to Jupiter and Europa. We talked about Europa, the interesting things about Europa. And then we talked about a little bit about Jupiter, very quickly about Jupiter. And so the next video, I'm going to piggyback off a lot of the stuff we talked about here. Next video is going to say, okay, these are some things you could look at. And I think you can tell already what I'm going to talk about is the stuff we don't know about Jupiter and about Europa is stuff that you could use for your science objectives. Alrighty, so thank you for listening and get over to the next video. Yay. Thanks.